Hello, the title of my poster is Topological Classification of Submersion Functions, that is a work in collaboration with Francisco Brown. We say that two functions f and g from R2 to R are topologically equivalent if there exist homeomorphisms H from R2 to R2 and L from R to R such that this diagram is commutative. Two regular foliations f1 and f2 are topologically equivalent if there is a homeomorphism H of R2 onto itself carrying its leaf of f1 onto a leaf of f2. In the case when H and L are orientation-preserving homeomorphisms, then we say that the functions f and g and respectively the foliations f1 and f2 are all topologically equivalent. If f and g are two submersion functions, then as we know, f and g define regular foliation of R2 whose leaves are the connected components of the level set of f and g respectively. If f and g are topologically equivalent, then the respective regular foliation of them are topologically equivalent. In fact, this implication is also true for all topologically equivalents, but the converse is not true even in the polynomial case. So, the main objective of this work is to introduce the class of linear-like submersion functions and provide conditions for the validity of the converse implication for functions inside this class. We say that P is a linear-like submersion function if P is a submersion of the form like this, when R and X are C-infinity real functions. In the case when the zero set of S is finite, then we say that P is a finite linear-like submersion. Now some preliminaries. Two leaves L1 and L2 of a regular foliation F in the plane are inseparable before any cross-sections sigma 1 and sigma 2 through L1 and L2 respectively. There is another leaf L3 intersecting sigma 1 and sigma 2. We say that a leaf L is a separatrix if it lives in the closure of the set of inseparable leaves. Each connected component of the complement of the set of separatrices of F will be called a canonical region. A chordal relation of a triple of three different leaves is one of the 5 different ways in which they can divide the plane. In the first 3 cases here, one leaf separates the other one. And in the second 2 cases here, they define a positive and a negative cycle respectively. Giving two subsets U and V of leaf of two regular foliations of the plane, we say that they are isomorphic if there is an bijection G between them, such that for any triple of different leaves in U, the chordal relation of them and the image by G are the same. In the case when the sign of the cycles are reversed by G, then we say that U and V are antisomorphic. A separatrix configuration of a given regular foliation F if the set of separatrices together with one leaf choose in each canonical region. In fact, we have that the separatrix configuration is a complete topological invariant. In fact, we have that two regular foliations F1 and F2 are all topologically equivalent if and only if the separatrix configuration of them are isomorphic. And they are topologically equivalent if and only if the separatrix configurations are isomorphic or antisomorphic. The description of the regular foliation given by a linear-like submersion P is as follows. From now on, VA will be denoted the vertical straight line x equal to A is a real value, and by ZP the set of zeros of x. So the complementary set of ZP with respect R is a disjoint countable many union of open intervals AI, BI. So for each real C, the level set LC of P if given by the disjoint union of these two sets here. The first one is the graphic of a function NC, whose expression is this, and the second one is a straight line given by this set. So the leaf of the foliation given by P are completely described as being of two types. In each non-empty strip, there exists exactly one connected component of LC given by the graphic of the function NC, that is a curve, straight to this interval here, for any real C. And for each x in ZP, the vertical straight line Vx is a connected component of LC, and C is the value of R in X. So we prove that letting C be the value assumed by P in VAI, then the graphic of the function NC defined in this interval is inseparable to VAI. Respectively, if we consider the straight line VBI. And the collection of the above leaves are the inseparable leaves of the foliation. So according to these propositions, we have the separateness configuration of the regular foliation given by P in each non-empty strip like this. For example, if we consider this strip, then the separateness configuration is this, and in this other strip, the separateness configuration is this. And in the other strips, the separateness configurations are these four or these others two ones. In all the cases, the inseparable leaves are the thick leaf. The bifurcation set of a finite linear-like submersion P is the set of denoted by BP, and we prove that this set is equal to the values of R in each zeros of X. And our main results are the following. We prove that two finite linear-like submersions P and Q are all topologically equivalent if and only if their bifurcation sets are empty or the following condition holds. The first one says that the regular foliation given by P and Q respectively are all topologically equivalent, and the second condition says that there is an increasing bijection sigma between the bifurcation sets such that this condition holds for each real C, that is a bifurcation value of Q, and H is an all equivalent homeomorphism between the regular foliations given by P and Q respectively. In the case when the bifurcation set of P is a singleton, therefore there exists a real value M that is not a bifurcation value of P and an extension of sigma to an increasing bijection sigma bar like this, such that this condition holds. And we have too the following corollary. We prove that two finite linear-like submersions P and Q are topologically equivalent if and only if their bifurcation sets are empty or the following conditions holds. The First conditions say that the respective regular foliations of P and Q are topologically equivalent, and the second condition says that there is a monotone bijection sigma between the bifurcation set of P and Q respectively, such that this condition holds for each bifurcation value of Q and H is an equivalence homeomorphism between their regular foliation of P and Q. So according to the last corollary, we can prove that these final linear-like summations P and Q given by this are now topologically equivalent. In fact, suppose that P and Q are topologically equivalent. Then, according to the last corollary, the conditions A and B must be satisfied. In fact, the conditions A is satisfied because the separatist configuration of the foliation given by P, that is it, and the separatist configuration given by the regular foliation of Q, that is other ones here, are isomorphic. So the regular foliations of P and Q respectively are all topologically equivalent. But the existence of a monotone bijection sigma between the bifurcation set of P and Q respectively such that this condition holds for any bifurcation value of Q and H, an equivalence homeomorphism between the regular foliations of P and Q respectively will be a contradiction because it implies that H must keeping the colors in the separatist configuration of P and Q respectively, and then H doesn't preserve chordal relation. So this is a contradiction, and so the functions P and Q are not topologically equivalent. So these are some references of our work, and thank you for your attention.